All right, we're going to go ahead and look at an example that uses some that involves uh, motion. This is going to be like a linear motion problem. So this is throwing a ball in the air. And this is going to be an example where we compare average velocity to instantaneous velocity and basically verify the mean value theorem for this real world model. So suppose you throw a ball in the air from an initial height of 2 meters and with an initial upwards velocity of 24 meters per second. Now, when you throw a ball in the air, as long as we are not paying attention to any like air resistance or friction, that might occur from that, if the only force we're considering is the force of gravity pulling down on that ball at a constant, with a constant acceleration downwards, then it turns out the height of the ball in meters after t seconds will be given by this equation. So the negative 4.9, that's half of 9.8. Negative 9.8 meters per second squared is the constant downwards acceleration of due to gravity. The 24 comes from the initial velocity, and the 2 here on the end comes from the initial height at time t equals 0. So, by the way, that equation, why exactly that is the equation, that will be justified later in the semester after we learn about integration, which is in chapter 5. Then we'll justify why it is that this is exactly what it is, and we'll prove this based on the assumption of constant acceleration. So, first thing we want to do here is find an average velocity. We're going to take the interval from 0 seconds to 2 seconds. So the average velocity, I'll represent that as V, AVE, as just an abbreviation for average. So this is V average. This is going to be our height at 2 seconds minus our height at 0 seconds. That's the change in overall height. We're going to divide that by the change in time. So that'd be 2 minus 0. So then if you evaluate, I won't go through the process, but you pull out your calculator. You can evaluate this function at 2, sticking 2 in for time, 2 in for t, and you get a height of 30.4 meters minus at height 0, of course at 0 seconds, we have our initial height of 2 meters. And, if you evaluate this function at t equals 0, you'll find it equals 2. So 2 meters divided by 2 seconds minus 0 seconds. So here we have 28.4 meters divided by 2 seconds. And this is 14.2 meters per second. So 14.2 meters per second is the average velocity of the ball. Vertical. This is a vertical velocity because this is the ball is going up and then coming back down. So on average, in the first 2 seconds, it's going up because this is positive at 14.2 meters per second, average. Now, the next part is to verify the mean value theorem by finding a time t within this interval 0 to 2 when the instantaneous velocity equals the average velocity. So this is exactly like what we were doing before, finding a time in the interval when the instantaneous rate of change equals the average rate of change. In other words, tangent slope equals secant slope. Okay, so that's like the same. This is the visualization of what we're doing right now, except now we're talking about it as velocity. So what we need to do is find the velocity as a function of time. So v of t, the velocity is going to be the rate of change in height. So h prime of t. So the rate of change in our height. So I've got to take the derivative of this function. So we'll just use the power rule here. So negative 4.9 times 2 is negative 9.8. And then times t to the power 1. And then plus the derivative of 24t will be 24. And then the derivative of plus 2 is plus 0. So we have negative 9.8t plus 24. So that is our velocity as a function of time. So now what we want to do is figure out when does v of t equal 14.2. When does the velocity equal 14.2 meters per second, right? So we'll take v of t and set it equal to 14.2. So we'll write negative 9.8 t plus 24 equals 14.2. Solve this equation. Subtract the 24. Oh, we actually get negative 9.8 t equals negative 9.8. So t would have to equal 1 second. And that's the answer here, folks. We discovered that actually when t is equal to 1 second, that is a moment in time when the instantaneous velocity given by the derivative of the function, of the height function, is equal to the average velocity on the interval from 0 to 2. So the fact that this 1 second is exactly halfway between 0 seconds and 2 seconds, by the way, is coincidence. That is not the way it always works. So do not expect that to happen again, ever. It seems like an unusual situation. Just the numbers happen to work out this time such that that is what we got. But in general, where on the interval the instantaneous rate equals the average rate depends entirely on the shape of the function, and it's certainly not always going to be halfway between the two. So just wanted to warn you about that. Please don't make that conclusion.